Hi, good morning. I wanted to talk about the Haber process today, and we will begin now. So the Haber process is a process by which nitrogen from the air combines with hydrogen that has been derived from natural gas, such as methane. The combination of nitrogen with hydrogen produces ammonia. The reaction between the nitrogen and the hydrogen is reversible, and when ammonia is produced, it is an exothermic process, meaning that heat is evolved. Nitrogen, one molecule of nitrogen combines with three molecules of hydrogen to provide two ammonia molecules, and 92 kilojoules of energy is evolved. The flow diagram for the process is as shown here. Nitrogen is extracted from air by fractional distillation, and hydrogen is derived from the natural gas. They are combined with each other in a 1:3 ratio as dictated by the chemical equation. So for every 1 part of ammonia, you need to supply 3 parts of hydrogen in order for the reaction to be successful. They are combined in a chamber at a temperature of 400 to 450 degrees Celsius at a pressure of 200 atmosphere, and an iron catalyst is required. With these conditions, you will get a high percentage of conversion of the nitrogen and hydrogen to ammonia. However, some of the gases will remain unreacted. So after the chamber where the gases have reacted, the resultant gases are cooled, and the ammonia that is formed will be condensed into liquid. The remaining nitrogen and hydrogen that was not reacted will be recycled and passed through the chamber again. Now, these conditions were selected based upon the Le Chatelier principle, in addition to looking at kinetic factors. Now, let us go back to this original equation. We can see that we want the reaction to go to the right. Because we have 4 molecules over here on the left, and we have 2 molecules on the right, it would suggest to us that a high pressure would favor a forward direction. So let us look at the Le Chatelier principle. A second. So if we look at the Le Chatelier principle, we would see, we would see that a high pressure would have actually forced the reaction to go forward, because when the pressure is increased, the system is going to want to react to counteract that high pressure. Now, because there are 4 molecules here and there are 2 molecules here, it benefits the system to produce more of these, because with the less molecules being produced, the pressure will be lowered. So high pressure would have actually favored a right shift. The problem, however, with generating high pressures is that it takes a lot of money for you to develop the reaction vessels that are able to sustain those high pressures. So a lot of time, even though the Le Chatelier principle suggests that a high pressure would be good, we have to consider what is the economic cost of generating that high pressure. So I'll just make a note of that. So economic cost is great for generating that high pressure. Hence the reason why they have done a compromise with a pressure of 200 atmosphere. This is a compromise where it's high enough to cause a right shift to take place, but it also isn't too high, so it isn't too expensive to generate these pressures. The temperature, the high temperatures of 400 to 450 degrees Celsius. So let's just see why this was chosen. As we see here, the forward reaction is exothermic. That means that the backward reaction would be endothermic. If you increased the temperature of this system, the system would want to go to the backward direction, right? So considering Le Chatelier's principle again, let us just write that the high temperatures, they actually favor a left shift, which is not good. But what we have done, what we also have to look at is that we have to consider the rate. However, it increases the rate. So we don't only look at the equilibrium, and we don't only look at the Le Chatelier principle. We must also look at the rate. How fast does the reaction take place? So this temperature of 400 to 450 degrees Celsius was selected to favor a fast rate for the reaction. The temperatures, if it was higher, it would have actually done more of a left shift, but this 400 to 450 is actually a compromised temperature that gives us a good equilibrium, and it also gives us a very good rate. So with these in mind, and with these conditions, we can actually get a good conversion for nitrogen and hydrogen. Now, why do we have the iron catalyst? Now, the catalyst does not affect the equilibrium, right? So whenever you introduce a catalyst, it's not for the purpose of shifting the equilibrium to the right or to the left. The purpose of introducing the catalyst is to increase the rate. So that is why the iron catalyst was added. And at the end of this process, we will produce our liquid ammonia. Let's look more at how the hydrogen gas was produced. It is said here that it was produced from the natural gas. So hydrogen gas is obtained by reacting methane with steam over a nickel catalyst. This is called steam reforming. So here we have methane, here we have steam, and we would assume that the nickel catalyst would have been somewhere here. And what we have is that the ammonia and the water combine to give us carbon monoxide and our 3 molecules of hydrogen. The nitrogen gas is obtained from air that has been liquefied, and then there is fractional distillation done. Please remember that air has many different gases in it. It has CO2, it has argon, it has nitrogen, among other gases, but we are only interested in getting the nitrogen out of the air. So we have to first convert that air into liquid air and then do fractional distillation to separate the nitrogen component from it. Now, according to the Le Chatelier principle, a lower temperature and a higher pressure would have increased the yield of ammonia. However, a temperature that is too low would slow the rate of the reaction, and high pressures are costly as materials must be strengthened to withstand the pressure to resist the risk of explosion. Thus, a compromise is reached where the temperature is not too low nor too high, and the pressure also is not too high, but high enough to shift the equilibrium position to the right. Under these conditions, the conversion rate for each cycle is 15%. However, it occurs quickly, and the unreacted gases are recycled to improve the efficiency.
You have likely produced ammonia in the laboratory from the thermal decomposition of ammonium chloride or from the reaction of ammonium and hydroxide ions. Have you ever wondered how ammonia is produced on an industrial scale? In this lesson, we will learn about the Haber process to produce ammonia, developed during World War I by Fritz Haber and Carl Bosch. For their efforts and contributions to developing large-scale industrial processes, they were awarded with Nobel Prizes in chemistry. The Haber process is the industrial process for the manufacture of ammonia from hydrogen and nitrogen. Hydrogen is obtained from the reaction of methane and steam, producing carbon monoxide as a byproduct. The hydrogen produced from this reaction also reacts with oxygen from air, producing water and leaving nitrogen behind. Recall that air is 77% nitrogen. These gases are then compressed and delivered to the reactor, where ammonia is produced. These gases are then cooled down and ammonia is liquefied, ready to be tapped off. Unused hydrogen and nitrogen are recycled back to the reactor. Let's revisit this reaction again. Note that this is a reversible reaction and that the forward reaction is exothermic. The Haber process uses Le Chatelier's principle to maximize ammonia production while keeping operating and production costs in mind. Le Chatelier's principle tells us that increasing pressure will favor the side with fewer moles. For our case, the production of ammonia. It would make sense to conduct the reaction at a very high pressure, but we must also remember that it is expensive to build and operate a plant that can withstand such high pressures. Therefore, a compromise pressure of 200 atmospheres is used. Let's keep Le Chatelier's principle in mind. What do you think is the best temperature conditions to maximize ammonia production? Please pause the video to think about this and resume once you are ready. Since the forward reaction is exothermic, it would make sense to conduct this reaction at a low temperature. The compromise temperature is 400 to 450 degrees Celsius, which is not exactly low, but not too high. If a low temperature were used, the rate of reaction would be very slow, though the exothermic reaction would be favored. It would actually take a long time for equilibrium to be reached, so a compromise temperature of 400 to 450 degrees Celsius ensures that the reaction proceeds with sufficient yield. The yield of this process is 10 to 20%. Remember from the introduction that unused gases are recycled, so no reactants are wasted. As well, an iron catalyst is used in this process. The presence of the catalyst does not affect the position of equilibrium, but increases the rate at which equilibrium is reached. In conclusion, the Haber process is the industrial process to produce ammonia from hydrogen and nitrogen. It is conducted at 400 to 450 degrees Celsius and at 200 atmospheres in the presence of an iron catalyst. These are compromise conditions in order to maximize ammonia production and economic profit.
Okay, so as we have just seen, we should be able to answer this checkpoint A that asks us to state the following conditions that would cause a shift in the position of the equilibrium left to right or no change at all. As we saw before, if we increase the temperature, according to the Chatelier principle, the system would try to decrease the temperature by going in the backward direction. So this would cause a left shift. If we decrease the pressure, the system would want to increase it. Now, if we go back up to the equation, there are 4 particles over here, there are 2 here. If we wanted to increase the pressure, it would make sense for us to go in the backward direction so we can create 4 particles, and these 4 particles will collide with the walls of the container and will generate a higher pressure for us than if we had 2 particles on this side colliding with the walls of the container. The pressure generated would be less with 2 particles than with 4. So as it says here, if we decrease the pressure, the system would want to increase it. And so the system would want to have a left shift in order to get that pressure to go back up. And in terms of adding a catalyst does not change the position of equilibrium. What a catalyst does is that it causes the equilibrium to be established more quickly. Now, in terms of the uses of ammonia, we look at some of them here. The reason why the persons who invented this Haber process were awarded the Nobel Prize in chemistry is because this process revolutionized the entire world, right? It caused, it gave persons the ability to create fixed nitrogen without having to depend upon the nitrogen cycle. So prior to the Haber process, we would have to depend upon the nitrogen cycle, whether it is by lightning or whether it was a nitrogen fixing bacteria to be able to produce ammonia and nitrates for us. And plants need nitrates in order to produce proteins. Now, in the case of the World War II, where there was widespread famine, it was not adequate for us to sit and wait on just the nitrogen cycle. So the 2 scientists who developed this process allowed fertilizers to be made so that fixed nitrogen could be added to the soil that could increase the plant yields and could feed a population that was basically facing famine. So that's the reason why they were awarded the Nobel Prize. So the uses of ammonia, as it says here, is for the manufacture of fertilizers and or it is used as a fertilizer itself. Ammonia also is used as a source of protein for livestock. It is used in the manufacture of nitric acid, drugs, and various textiles. And it's also used in water treatment for the control of pH. I'm going to just show you a short video that will give you some more uses of ammonia.
We have previously learned about the Haber process as the industrial method to produce ammonia. Why do we need such large quantities of ammonia, and why is it so important? Ammonia is used to produce fertilizers, nitric acid, and certain household cleaning products. Ammonia is also used as a starting material for explosives and many pharmaceutical products. Nitrogen is important and essential for plant growth. Although air is approximately 77% nitrogen, plants cannot breathe it in. Instead, it must be dissolved in water and absorbed through their roots. This is done naturally by lightning and by certain types of bacteria, though it does not happen often or fast enough to sustain crop growth and hence food production. Fertilizers are used to increase the nitrogen content of soil, or, in other words, make it more fertile. Livestock manure has been traditionally used as natural fertilizers, but this has become too difficult provided the massive size of many crop fields. Two very common artificial fertilizers are ammonium nitrate and ammonium sulfate. And you got it, they are made from ammonia. Ammonium nitrate is made from ammonia and nitric acid. Ammonium sulfate is made from ammonia and sulfuric acid. The constant production of these fertilizers is very important to sustain global food production. Nitric acid is also manufactured from ammonia in a series of steps. First, ammonia combines with oxygen over a platinum catalyst to produce nitrogen monoxide and water. Then, nitrogen monoxide further combines with oxygen to produce nitrogen dioxide, which is a brown gas. Lastly, nitrogen dioxide and oxygen dissolve in water to form nitric acid. By combining these equations, we get this overall reaction to produce nitric acid from ammonia. Nitric acid is used in the production of ammonium nitrate and other nitrate-based fertilizers. It is also used as a starting material for many explosives, a common one being TNT or trinitrotoluene. Nitric acid is also very important for the pharmaceutical industry. It is also used to produce certain dyes. These dyes are used as food coloring in the textiles industry and even as indicators. Royal water, or aqua regia, is a mixture of 1 part concentrated nitric acid and 3 parts concentrated hydrochloric acid. In the laboratory, it is used to clean glassware, but a much more interesting application is its use in the purification of gold and platinum. Very dilute solutions of aqueous ammonia, approximately 5 to 10% weight by volume, are commonly sold as household cleaning products. You may have encountered household ammonia in your own kitchen and in your bathroom cleaning products. So to recap, ammonia is used for the production of cleaning products and pharmaceutical products. Even more importantly, ammonia and the fertilizers we produce with it are vital to sustaining global food production. Our world population is growing massively, and without such agricultural technology, we would be even less able to prevent famines.
So as it said, as we had discussed before, this Haber process was a life-changing process that allows us to produce foods on a large agricultural scale to prevent famine without having to depend on just the nitrogen cycle to produce fixed ammonia for us. Now, let us just consider the final part of this topic, which is to look at the environmental impact of the ammonia industry. So one of the impacts is that it causes atmospheric deposition. So ammonia gas itself, if it gets into the atmosphere, can fall to the ground over land during rainfall, and this can result in terrestrial eutrophication. Eutrophication is the enrichment of the nitrogen content, whether on land or in water. In this case, terrestrial eutrophication is referring to the enrichment of nitrogen content on land. This ultimately causes the disruption of plant ecosystems, with a few common fast-growing species dominating over a greater variety of plants, often of conservative value. The next impact, which is also linked to the first, is eutrophication of water bodies. So overuse of ammonia fertilizers on farms can cause the fertilizers to get washed off, and eventually it will end up into the rivers and the streams. These fertilizers are water soluble, and excess is leached from the soil during rainfall or irrigation, causing the bacterial levels in nearby water bodies to increase substantially. This large increase in bacteria robs the water body of adequate oxygen and causes other aquatic life to die. I'll expound on the eutrophication in a bit. Also, in terms of when there is acidic soil, it says that the overuse of fertilizers can eventually cause the soil to become acidic. And when the soils become acidic, it cannot support several crops that are needed today, and the soil must be neutralized before any more crops are planted. This neutralization must be done on a continuous basis to ensure the viability of the soil. Another impact is air pollution. High concentrations of ammonia in air can damage vegetation such as lichen and moss. It also contributes to the formation of haze in the atmosphere, which reduces visibility, and the formation of particulate matter, which can cause respiratory problems. This checkpoint B is what I would like for you to complete in your own time. And when we have our next class, we will be discussing this checkpoint. Please ensure that it is completed. So I will now show you a video of the impacts, the environmental and social impacts of the ammonia industry on the environment, which will include some of what we have discussed before.
The Haber process has enabled ammonia to be produced on an industrial scale. Ammonia, as we know, can be used to make fertilizers. The large-scale production of ammonia-based fertilizers, such as ammonium nitrate and ammonium sulfate, has made it possible to sustain global food production. Although it may seem as if this is a good thing, there are actually very serious environmental and social consequences from the overuse of these fertilizers. Fertilizers must be dissolved in water before they can be absorbed by plants through their roots. This can happen from manual watering or rainfall. Heavy rainfall, however, can wash dissolved fertilizers into large bodies of water, such as rivers and lakes. In fact, even without heavy rain, dissolved fertilizers can still leach from soil into water. We have to remember that there are also aquatic plants, or plants that grow exclusively in water. The presence of these fertilizers will cause them to grow faster than usual. This is called eutrophication. The main issue here is that most of these aquatic plants are not a food source for humans. These plants just grow and die and they decay. Dead and decaying plant matter blocks sunlight from reaching live aquatic plants and thus prevents photosynthesis from occurring. So these plants also die and decay. In fact, it doesn't end here. Aerobic bacteria, which require oxygen to live, feed on these decaying plant matter. These bacteria then also grow faster than usual and consume a lot of oxygen. This then decreases the concentration of dissolved oxygen in water. So fish and other aquatic organisms suffocate, and die. Now that we've looked at the environmental consequences, can you think about a few social consequences? Please pause the lesson to think about this and resume when you are ready. Fish are a main food source for some communities, so fewer fish means less food for people who live in these communities. As well, some communities rely heavily on the fishing industry, so fewer fish caught could mean that many people will struggle to make a living. Dissolved fertilizers can also cause algae or microscopic aquatic plant organisms to grow quicker than usual. When they grow too quickly, a phenomenon known as an algal bloom occurs. An algal bloom could span over many kilometers in a large body of water, thus blocking sunlight from reaching other aquatic organisms. The same scenario occurs. Aerobic bacteria feed on all of the dead and decaying algal matter and are then able to thrive and multiply. They consume oxygen and decrease the concentration of dissolved oxygen in water, suffocating aquatic organisms.
Right, so that is basically the end of this topic for the Haber process. Please remember to complete checkpoint B as it concerns this.